If you were in discussion class yesterday, you know about this. Since between now and next Tuesday, we have no additional class meetings, I've decided to postpone the turn-in date for bonus quiz 2 from yesterday till next Tuesday, and quiz 3 not next Tuesday, but a week from next Tuesday. This will give us ample time at least to get through chapter 22, our present chapter on electrochemistry. And today, if I'm a little groggy, it's just because I stayed up late last night to watch some interesting activities. It appears that, among other good things, we also got the board fixed. I wonder if that was by congressional action. Now then, to pick up from our point of departure, sodium clobbers water. Zinc, copper do not. Upshot, since sodium can reduce water, sodium is a stronger reducer than the conjugate oxidizer of pH 7 water, which is hydrogen and hydroxide ion, given that hydrogen and hydroxide ion are the materials produced by sodium reducing water. Since zinc does not clobber water, zinc being oxidized to hydrated zinc ion has got to be a weaker reducer than this reducing system. Zinc doesn't reduce this, so it must be true that hydrogen and hydroxide ion can reduce this. Now then, are you the wallet person?
Yeah, I'm the wallet person.
That's $2. Carry on.
Thank you.
Then, zinc in 1 molar sulfuric acid solution, copper in 1 molar sulfuric acid solution. Zinc goes readily by oxidation, because of oxidation by hydronium ion. Products, hydrogen and water. Copper does not reduce hydronium ion, not oxidizable by 1 molar sulfuric acid solution. In fact, copper is not even oxidizable by 9 molar sulfuric acid solution, which we've noted again on the board. I've got here copper standing in 9 molar sulfuric acid solution. Just to confirm that copper does nothing in 9 molar sulfuric acid solution. We already know that zinc is a stronger reducer than copper because of what we did with zinc and copper and zinc ion and copper ion previously. But now we know that although hydronium ion is capable of oxidizing zinc, copper is not capable of being oxidized by hydronium ion. So, we can put copper being oxidized in the presence of water, become the hydrated copper ion, as a reducing system, which is weaker than this reducing system. Since copper does not reduce this, it must be true that the conjugate reducer of this, which is hydrogen and water, is capable of reducing hydrated copper ion. So we've got one remaining investigation to do with copper, which indicates a reaction. I've got here another copper strip in a separate beaker. We'll treat this with some 6 molar nitric and see if we can get something out of this. Now, copper is not a particularly strong reducer, but we will see that it is oxidized in this system. We'll let it stand a bit while we talk about the chemistry of the system. because in yesterday's discussion class gathering, what you were focusing on is learning the chemistry, which underlie the rules for developing equations for half reactions. Rules which allow you to derive half reactions. And you recognized that a number of these rules depend on acid-base chemistry. Are we getting something in the copper nitric acid system?
Yes.
If for no other reason, we can see the development of the color which is characteristic of hydrated copper ion. Many of you by now are in assignment 6 in the laboratory where you're doing work with hydrated copper ion, so you're already familiar with this ion because of its characteristic color in water solution. Tell me, let's see, who'll pick on today? We'll pick on you. What do you see occurring on the surface of the copper strip?
There seems to be some white stuff.
White stuff. White stuff is being reported on the surface of the copper strip.
It's, yeah.
What do you say?
I kind of agree, but
You kind of agree.
it looks like it's not as faded.
Remember, the election is over.
It's I don't have to be, yeah. Yeah, I agree.
You agree. What do you see? What do you see occurring on the surface of the copper strip?
It's cloudy white particles kind of near the surface of the strip, yeah.
White particles near the surface of the strip.
Looks like there's a tiny, tiny bit of bubbling, but...
Bubbling! Aha!
Yeah. I see.
Yep, what?
I see a white precipitate and
A white precipitate.
or
I don't see any white precipitate at the bottom of the beaker.
yeah, particles floating around.
Particles floating around. What do you see? Surface of the copper strip.
It looks like it's dissolving.
Dissolving. Well, you told me what's happening to the copper. I want to know what's happening on the surface of the copper strip.
It's like a gas is being...
A gas is being evolved. That accounts for the bubbles. Now, this gas is not a nice stuff. So I'm going to stop this reaction. But the reason why you see a cloudy appearance inside the system right next to the copper strip is the vigorous evolution of bubbles. A gas is being produced by this redox reaction. Notice the distinct change in the appearance of copper, because as this reaction takes place, we keep on exposing fresh copper to the ingredients of the oxidizing materials in the solution. It's a simple way to clean copper. Unfortunately, it leads to the disappearance of copper as well. All right. Since our intent in the main is to recognize how to develop equations for redox reactions, and since we have already written the equation for the reaction corresponding to the oxidation of copper, which I've already taken the liberty of writing in our table, let's get at the equation for the half reaction which corresponds to reduction. What is getting reduced? Well, PSI nitric acid solution. Hydronium ion, nitrate ion, each present at a molarity of 6, because this is 6 molar nitric, and water molecules. Is water doing the oxidizing? Can copper reduce water? No. Is hydronium ion doing the oxidizing? Copper oxidized by 9 molar hydronium ion? No. So should copper be oxidized by 6 molar hydronium ion? No. Well, that only leaves one other thing in here to get reduced. Nitrate ion. So it's a good bet that whatever this gas that's being produced must contain nitrogen in its composition. Now, it is true that nitrate ion, since its component atoms are nitrogen and oxygen exclusively, can be reduced to a whole bunch of different materials. You can reduce nitrate ion to nitrite ion. You can reduce nitrate ion to NO2. You can reduce nitrate ion to NO. You don't need to write these down. You can reduce nitrate ion to nitrous oxide. You can reduce nitrate ion to nitrogen. And if you have a really strong reducer, you can reduce nitrate ion in the presence of a system which also contains hydrogen atoms all the way to ammonium ion. And there are other materials, such as N2O3. A lot of possibilities. The upshot of which is, if we want to know what this gas is, given that the only conclusion we've been able to reach in a justifiable fashion is that it's something which has got nitrogen in its composition, because nitrate ion is getting reduced, because we know we don't produce an oxygen by oxidation, we produce that by reduction. But in this case, to produce oxygen from nitrate ion, we'd have to oxidize nitrate ion, not reduce it. So in order to find out what this gas is, we'd have to catch it and analyze it. So let's imagine we did catch it and analyze it. We'd find out that it's a mix of these two gases with some of this. So we'd be stuck to write an equation, because this would be a non-stoichiometric mix unless we know the ratio of this to this to this produced as this gas is being formed. But analysis further shows the gas is mainly this. So let's take this as the only product. Not an unreasonable statement, given that analysis shows the gas is mainly this. So we'll take it as only this. So what can we start with? We can start with this. Nitrate ion is getting reduced, and we're taking the reduction product to be nitric oxide. How do we develop the reaction equation? We look at what we have so far and let this statement talk to us. What does this statement tell us as it talks to us? It tells us that as a nitrate ion is converted to an NO molecule, two component oxygen atoms of the nitrate ion go someplace. What is the nature of these component oxygen atoms of nitrate ion which went someplace? To get at this, let's write a Lewis picture for nitrate ion, because we know this reaction involves nitrogen-oxygen bond breaking. So we look at the nitrate ion's Lewis picture to get a handle, a more direct handle on the bonds which break. The bonds are all equivalent, remember that. There is no double bond and no single bonds. This is a resonance stabilized structure. Every NO bond is equal in length and strength. Every NO bond is stronger than an NO single bond, and every NO bond is weaker than an NO double bond. Every NO bond is shorter than an NO single bond and longer than an NO double bond. And we also know when these bonds break, they will break in solution such that the electrons which were previously shared between atoms, the previously bonding electrons, will be parceled into the valence environment of the atom of greater electronegativity. So we can use this picture to show us that the oxygen atoms, which are cleaved from the nitrate ion by this reaction, have this valence electron structure. What's the oxidation state for this oxygen atom? What is it? 2 minus. Now comes the chemistry. Well, more chemistry. We've done chemistry. Tell me, from our knowledge of acid-base chemistry, what do you know about this stuff from an acid-base standpoint? If you don't remember, get out the acid-base table. This is the number 1 strongest base listed in our acid-base table. What's its name? Oxide ion. So we can, in fact, treat this nitrate ion conversion to NO as a reaction which, as it occurs, puts oxide ions into solution. And oxide ions are potent bases. What do potent bases do when they're placed into a chemical system? I want an answer that's always right. They will react with the strongest acid present in high concentration. Tell me, in this solution, what is the strongest acid present in high concentration? It's hydronium ion, 6 molar. So here we go. Now, more acid-base chemistry. This is a strongly acid solution. So how many hydronium ions will be murdered by 1 oxide ion?
2.
Because if oxide ion murders 1 hydronium ion, what do we convert the oxide ion to? Hydroxide ion. You going to make hydroxide ions in strongly acid solution? No. Not today, not tomorrow, not ever. And when hydronium ions lose H+, they become water. How many waters are made by this reaction? How many? 3. 2 hydronium ions get deprotonated, and each of these H pluses land on oxide to make another water molecule. Back to the nitrate ion. As this conversion takes place, how many of these oxide ions are going into solution? 2 of them. So how many hydronium ions do we need? 4. And so in addition to NO gas, what else are we making? 6 waters. And guess what? By chemical analysis, we have now established for this statement material balance. So to turn this into an equation, we need to establish charge balance. As things stand, sum total of charge on the right side of our almost equation is how much? 0. Sum total charge on left side is 4 moles plus, 1 mole minus. That's 3 net moles plus. So how many moles electrons do we have to add to be sure that when it adds up we get 0 charge? 3. See? This is not hard. And guess what? When you put this multiplier in front of electrons, it always keeps with total change in oxidation number. You remember the oxidation number for nitrogen and nitrate ion? To get at the oxidation number, we'd have to cleave this bond also, and we'd find out this is 5 plus. What's the oxidation number for nitrogen in NO? 2 plus. If I want to go from 5 plus nitrogen to 2 plus nitrogen, how many electrons do I have to add? 3, all done. And now we're in position to if we wanted, couple this half reaction with this half reaction, that would require multiplication of this statement by 3, this statement by 2, and add them up. If we did this, we could then answer the question, as this transformation takes place, what happens to pH? Pretty obvious what happens to pH as this transformation takes place, isn't it? Does pH stay the same, go up, or come down? pH goes up because this redox reaction leads to a net consumption of hydronium, doesn't it? That drives the pH up. So now, to be systematic, we take this half reaction which we've just developed, write it in the opposite direction, and complete our short table. And there we have it. 6 half reactions. When we did this on Monday, we had only 4 half reactions written. Now we've got 6. So I'll repeat the question which I asked of you when we had the 4 half reactions, and say, with this table, the outcome of how many redox reactions can be predicted successfully? Yup! 30! 6 times 5. Either way you look at it. And if you play this game with the half reaction table we have in the notes, table 2, if my memory's right, it may not be, there are 42 half reactions. If there are 42 half reactions, you can check the count. If there are 42 half reactions in table 2, 45? 45 half reactions, that's even better. How many redox reactions can have their outcome successfully predicted by table 2 where we have 45 half reactions? What's the arithmetic we have to do to get the value? 45 times 44. That's a hell of a lot of reactions. See? Oh, good, you even did the arithmetic. Because again, as we reminded you before, what table 2 is, like our acid-base table, is a table that's full of thermodynamic stability information. Because when a reaction is spontaneous, what are you really realizing? The products are more stable than the reactants. That's what you're realizing.
How did you know that you're in a gas equation was the very least, like it should be at the bottom?
Well, what have we just found out? Was copper capable of reducing hydronium ion? No. Was copper capable of reducing hydrated zinc ion? No. Was copper capable of reducing water? No. You think copper is capable of reducing sodium ion? No. But is copper capable of reducing this combo? Yes. So this has got to be on the one on the bottom, because on the right side we've got here the strongest oxidizer, don't we? And the weakest reducer. Tell me, from this table, what reaction, what redox reaction could you construct from this table, which would be by far the most vigorous? Sodium in nitric acid solution. Woo! You make that one, you won't have a chance to get the hell out of the way. As soon as the sodium hits the nitric acid solution, I guarantee, boom! And away it goes. Now we got one more question to ask. We have recognized that in this oxidation of copper by nitric acid solution, nitrate ions getting reduced. But does it appear that nitrate ion was assisted by hydronium ion because hydronium ion consumed these so-called -2 oxidation state oxide ions? So the question is, which is is the stronger oxidizer? What can we do to find out? You think there are various things we could do to find out. Which is the stronger oxidizer, hydronium ion or nitrate ion? Well, I'll write a statement down as a result of a reaction. Pardon me, not as a result of a reaction, but as a result of an investigation. Zinc in 6 molar sodium nitrate solution is no reaction. What's that tell you? Does this tell you about the difference in oxidizing ability of hydronium ion versus nitrate ion? Was zinc oxidizable by 1 molar hydronium ion? Yes. Is zinc oxidizable by 6 molar nitrate ion? No. Who's the stronger oxidizer? Hydronium ion. But when it comes to copper, what we are realizing is you need both, because the hydronium ion nitrate ion combo has proved itself to be the strongest oxidizing system of all the oxidizers we've looked at. So let's go back for a moment to our copper strip standing in 9 molar sulfuric acid solution. If I were to place the copper in 6 molar sodium nitrate solution, just 6 molar sodium nitrate solution, would you expect any reaction? No. But what do you think is going to happen if I put some 6 molar sodium nitrate solution into the 9 molar sulfuric acid solution, which has the copper strip standing within? Reaction? Let's find out. See any color beginning to develop? Yes. Let's pick on you folks. See any gas forming on the surface of the copper strip?
For sure.
Yes.
You betcha. Because we now have the same reaction taking place as we did with the copper strip standing previously in the 6 molar nitric acid solution. If I leave this stand for another minute or so, it'll be the rather intense aqua blue color as we saw previously because of the presence of a fairly high concentration of hydrated copper ion. Now the main reason why NO gas is not something I wish to expose to the atmosphere is not that NO gas is toxic, but NO gas in the presence of atmospheric oxygen readily oxidizes to this stuff. This stuff is toxic. This stuff is a brownish colored gas. I think you remember that, don't you? Remember NO2, our NO2, N2O4 equilibrium system? Any of you as yet in laboratory get to assignment 7? In assignment 7, you will prepare some quite stable materials, specifically zinc sulfide, copper sulfide, and silver sulfide, with silver and copper sulfides being damn stable. But silver and copper sulfide look just alike. So if we give you a sample that's a brown-black powder and it's not water soluble, and you want to find out if it's silver sulfide or copper sulfide, or maybe silver oxide or copper oxide, because those are also brown, black, water insoluble powders, what are you going to do? Pure samples of these four materials are all fair game unknowns for 2046 Laboratory Assignment 9. And they look just alike. Brown-black powders, not water-soluble, will have no impact practically on water pH because they're of such low solubility. What are you going to do to find out? Or are you going to throw up your hands in disgust and say, I can't figure this out, it's too damn hard? Well, what you're going to do is to take advantage of what you will also learn in Assignment 8. Because Assignment 8 in 46 Laboratory is going to involve using 6 molar nitric acid, like we did here, as well as (16 molar nitric acid. Which do you think is the stronger oxidizing system? 6 molar nitric or 16 molar nitric? 16, more concentrated, nothing fancy about that conclusion. And you'll find out that either of these acids is capable of dissolving any of these materials. But straight hydronium ion will dissolve not this, but this and this. So if this brown-black stuff is hydronium ion soluble, you can draw a line of separation between these materials. Hydronium ion soluble, not hydronium ion soluble. And then by oxidation with this, if you have to distinguish between these two, what would you do to find out? If these materials are oxidizable by the potent system, 6 molar nitric, potent oxidizing system, 6 molar nitric or 16 molar nitric, because now you've got acid attack as well as oxidizer attack. How will you find out if you got silver sulfide or copper sulfide? Color, because the copper ion in solution will give you this nice blue coloration, won't it? You have a question?
Yeah, okay, well, 2 questions now. The blue color versus the brown color, does that apply for both copper oxide?
What brown color?
I'm sorry, silver forms a, does it form a color in solution?
Mm-mm.
Okay, so will copper oxide or copper sulfide form a blue color?
If you get them to dissolve, sure. All right, on we go. According to reports from discussion instructors yesterday, again, varying degrees of progress were made. So we're going to go back to question 2215, which is a continuation of this business of learning the rules for deriving half reactions and then understanding the chemistry upon which the rules are founded. This is part 3 of question 2215. In this case, we're considering the oxidation of zinc rather than copper or some other metal by 6 molar nitric acid solution. So we'll write ZO for oxidized in 6 molar nitric acid solution. We've just learned that nitrate ion hydronium ion combo is one potent oxidizing system, provided hydronium ion and nitrate ion are both present in appreciable concentration. And now, since zinc is a stronger reducer than copper, which we already know, we shouldn't be surprised to see that we can clobber nitrogen and nitrate ion to the extent of reducing all the way to 0 oxidation state nitrogen. Copper took it to +2 oxidation state nitrogen. The stronger reducer, zinc, takes it to 0 oxidation state nitrogen. Now we know what the half reaction is for the oxidation of zinc in acid solution. You see this note I wrote here? When we oxidize metals in acid solution, you almost always produce the hydrated metal ion as the oxidation product. If there's a Lewis base in there which reacts more strongly with the derived metal ion, then we'll have to tell you what the oxidation product is. But other than that, it's going to be the hydrated metal ion. And just about all hydrated metal ions are hexahydrates, like our hydrated zinc ion in this table, like our hydrated copper ion in this table, like hydrated aluminum ion and iron +3 ion in our acid base table. Tell me, since we have now finished developing this equation, showing the conversion of nitrate ion to NO, what do you think we're going to have to do to this equation modification-wise to account for this chemistry? In this case, are we having to strip all the -2 oxidation state oxygen? Yep. And in this case, from a material balance standpoint, if I want to make a nitrogen molecule by clobbering nitrate ion, how many nitrate ions do I have to clobber? 2 of them. And now I'm going to have to clobber all these -2 oxidation state oxygens, of which I now have 6 moles. So how many total moles of hydronium ion am I going to need? So besides nitrogen, what else am I going to make by this reaction? How many? All done, except for charge balance. What's the multiplier on electricity for this one? Oxidation state nitrogen and nitrate ion? +5. How many nitrate ions did we clobber? 2. And we turned them all into 0 oxidation state nitrogens. So what's the total change in charge? 10. It's not hard if you pay attention to the chemistry of the system. All right, we proceed. Part 4. It's also true that for a number of metal ions, hydroxide ion proves to be a fairly reasonable Lewis base. The consequence of which is I get not only hydroxide precipitates of a number of metal ions, and you're familiar with some, calcium hydroxide, which you've made in laboratory, which we've talked about here in class, aluminum hydroxide, magnesium hydroxide, copper hydroxide, zinc hydroxide, and then you found out that aluminum hydroxide can be dissolved by treatment with excess hydroxide ion because aluminum hydroxide is said to be amphoteric. And so you can dissolve aluminum hydroxide by converting it to aluminate ion. You can dissolve copper hydroxide by converting it to cuprate ion. You can dissolve zinc hydroxide by converting it to zincate ion. Those are simply the names for the hydroxyl complex ions of the respective metals. So, all right. I'll write this statement to show you that if aluminum is dissolved, or pardon me, is treated with 6 molar sodium hydroxide solution, the aluminum will dissolve by oxidation. And it will be converted to 6 molar sodium hydroxide solution. And it will be converted to aluminate ion. 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 And it will be converted to a to what you've learned in Assignment 4 laboratory is known as the aluminate ion. When we get to chapter 24, we'll learn that this is tetrahydroxodiaquoaluminate ion. More words. Who cares about that? Because if you got the formula, you got the most important part. So we'll just stick with the formula and still call it aluminate ion. What we want to do now is to turn this into a half reaction and develop the other half reaction. Well, I should think by now, if there's one thing you've all recognized for sure, if you're going to do any chemical analysis of a chemical system, what do you do first? How about that? And here we go. We have a system that's rich in hydroxide ion. We have a system that's rich in water molecules. So if we're going to turn aluminum into the aluminate ion by oxidation, in a system that's rich in water and rich in hydroxide ion, let's put them in the equation. They're there. And these are recognized as being components of this complex ion. Number of electrons produced, or liberated, I should say. Do you know, or did you learn in 2045, that the only positive oxidation state aluminum ever develops is +3? So there's the half reaction for oxidation of aluminum. Now then, what do you think is getting reduced? To support your ability to answer this question, I'll give you some more information. As aluminum is oxidized in 6 molar sodium hydroxide solution, with the aluminum converting to aluminate ion, a gas is liberated. What do you think the gas is that's liberated? You think it's sodium gas? You think aluminum can reduce sodium ion? You think any soft drinks contain any sodium ion? And you know many soft drink cans are made out of what? Aluminum. You want to make a soft drink can out of a metal that will reduce the contents of the can? Huh? These 1A metal ions are damn lousy, feeble, weak oxidizers, because they are derived from damn strong, powerful, potent reducers. So we got a choice. We're going to reduce water or hydroxide ion. And we told you a gas is produced. What do you think the gas product is? Hydrogen, because you're not making oxygen by reduction. You've got to make that by oxidation. So we can write this. Now you got a choice, because water and hydroxide ion are both hydrogen atom containing species. What's getting reduced? Is it water or hydroxide ion? Did we not find out that the production of hydrogen by redox depends on pH? Did we not find out that water will not oxidize zinc, at least not readily, whereas hydronium ion readily oxidizes zinc? What is the main difference between hydronium ion and water, beside the fact that hydronium ion has a charge? Hydronium ion is a much stronger
Base.
What are you talking about? I'm sorry.
Hydronium ion is a much stronger acid. Goody! Because in order to make hydrogen by reduction, you have to reduce +1 oxidation state hydrogens. So that's why it is correct to conclude that the best supplier of +1 oxidation state hydrogens is the stuff that's going to get reduced. That means the best, strongest acid. Which is the stronger acid, water or hydroxide ion? How about that? Have we got this half reaction in our table? We sure as hell do. So you can finish this one, and we'll pick it up from this point next time.